Welcome, everybody. My name is Jesse Trank. I'm an applications engineer here at Mastercam. And I'd like to thank you guys for taking the time to join our Dynamic Thinking Series webinars today. So today we're going to focus our discussion on technology for the die mold industry, and specifically the partnership between Mastercam and Makino. I hope to cover some interesting technology that we have inside of Mastercam and how it pairs nicely with the technology in the new Makino machines and their Pro 6 controller. So for this discussion, I have Greg Pozo with me. He's an applications team leader for their vertical machining. And he had a few general questions for me, and that we were going over, and we kind of thought it would be beneficial for everybody to listen in, and there's a lot of good information that we covered answering those questions. So we'd like to keep this open. Like I said before, if you have questions as we go through it, feel free to type them in the chat window, and we'll try to get to them when we can. At the end of the content that we're going over, we'll open it up, and I'll address any questions that I haven't answered yet, and as well as any new ones that come in. So, Greg, if you want to show your webcam yourself, then we can get started.
Thanks, Jesse, and thanks for inviting me to join this Dynamic Thinking webinar. I'd also like to thank all the attendees that are here today. Like Jesse said, my name is Greg Pozo. I'm the application team leader for die mold in Auburn Hills, Michigan. And I've worked at Makino for about 10 years, and I've seen what I would consider a process change in our industry. It's really surrounded around 5-axis. So we've seen an evolution of technology that's happening. So we at Makino like to call it 5XC. But basically what we're seeing is that, for instance, in our Pro 6 controller, our motion control technology has advanced quite a bit. We've seen our rotary table accuracies and performance increase a lot. We have a technology that actually checks collisions live at the machine for 5-axis motion. We call it collision safeguard, or CSG. We've also seen the cutting tool performances, better themselves through multi-flute cutters. We've also seen unique shaped tools coming out now. We call them hybrid tools. You might know them as barrel tools or circle segment tools, lens tools. So we have all this technology that's evolving and getting better. And we need more accurate tool path. We need better technology to take advantage of this. And really what kind of manages it all is the CAM system. And it's playing that critical role in pulling all these technologies together.
Yeah, thanks, Greg. So I think we'll jump into it here. And since we're going to be diving in and out of the software, I think we'll kill our webcams here so that we get the most bandwidth we can. But oops, I killed the display here instead of my webcam. All right, so Greg, why don't you get started? Hit me with some questions and see if we can get some answers to those.
Sure, great. So, at Makino, we work a lot with very complex 3D shapes, and, as you're probably aware, these 3D models are probably one of the most intense calculations that CAM systems have. And, as I was mentioning before, in our Pro 6 control, we have technology that's taken advantage of, how the machine is moving and to get that to work accurately and at its best performance. For a lot of our medium to small size molds, we're looking for calculation tolerances in the CAM system of about 1 micron. And what that does for us is it helps define a very accurate shape, and our control can actually run faster, more accurately with a better definition of the model. But obviously at that calculation tolerance, it can take longer times to process it. So I guess my question to you, Jesse, is, what are CAM systems, or what is Mastercam doing to kind of either reduce this or manage that calculation time so programmers are, being as efficient as possible?
Yeah. I mean, that's an awesome question. Something that comes up a lot, and I think our answer to that is, continuous improvement, right? That's an active area of development for us, and as technology progresses, our development team races to keep up and take full advantage of that technology to leverage it inside of our software to reduce calculation time. I mean, it's super critical when we're talking about high end machines, like your Makinos, right? We verified that in our lab here. We had a Makino D200Z and with the Pro 6 on it, and you know we could see that Pro 6 craves a ton of code and an extremely tight tolerance. I mean, it was easy to give it a loose tolerance like you would on some of the lower end machines and see that it was doing okay, but it really excelled when we gave it that tight tolerance and gave it that accurate code to let the control make the decisions instead of forcing the cam system, forcing it on the machine. The machine's fully capable of understanding how it needs to move. So release by release, we strive to reduce that calculation time. Things are only getting, more and more accurate. Your machines, you're not going where you're saying, oh, in 3 years we expect less accurate code. No, that's the exact opposite, right? You're only expecting more and more, accurate G code and let the control really perform. So, our QC team is set up with a huge set of automated tests, that, we run any enhancements or changes we make in the software, we got to run that through and make sure that we are in fact meeting the goal of reducing calculation time. We can't ever inflate calculation time. That would be a step in the wrong direction. We are getting better and better, at leveraging multi-core processing across the product. So that allows the user to stay productive while a toolpath is calculating in the background. And, like I said, it's a continuous improvement effort and it'll never be done. The thing that we have to realize as a CAM software company is that we can't live in a vacuum outside of, what these controls are. They're digesting our output. So we need to understand what those different machines and controllers need to see in code output, Makino being one of many, and our software needs to be flexible enough to suit all of them. So, that Makino craves that tight tolerance and accurate code. So as an applications engineer, I need to understand what needs these various machines have for lines versus arcs and the different tolerances and such, and be able to make recommendations to our resellers and to our end users. And a lot of that comes through partnerships with guys like you, Greg. So if I'm not familiar exactly with the control, reach out to you and figure that out. The technology is useless if you don't know how or when to apply it. And you really need to understand what that output's going to look like in Mastercam. So I think I'm going to jump into Mastercam really quick here and just show you, one of the tools that I really like. It's not brand new for 2021, but releases, it is new and it really makes things nice. So if I look at this raster toolpath I have here, and I'll go into the parameters real quick. So this is a mold cavity. If I look at the tolerance page, right, I'm at 0.01 millimeter. So not incredibly tight. If I look at the toolpath, it's a small surface. It's not going to take that long to generate. But if we move down, let's copy this below. And let's bump that tolerance down. 0.001. I'll regen. Now you can see this is kicking out to the multi-threading manager. It happened really fast. It's a small toolpath, nothing taking very long there. But if I turn off that toolpath, turn off that one, turn this one back on, are you seeing any difference there? Not really, right? There's no way to visualize that tolerance difference just by looking at the graphics screen. So a neat feature that I use all the time now is, let's turn this first one back on, is advanced display. So one of the functions of advanced display is to color code different segments of the toolpath from, rapids versus micro lifts versus entry motion, lead in, lead outs, that sort of thing, which is useful. But one of my favorite features of it is this endpoints display. if I turn on the endpoints, I can see the difference. I can actually see the pieces of G code, what each one of those segments represents, a G1, a G2, a G3, and really understand what that code's going to look like. So if I go down to this next toolpath and display that, you can see we're getting a lot more code, right? So I can see how much more accurate that code is and the points I'm giving the machine. Now, if I jump back in there, let's tighten this up even further, right? And now when I regen, it's probably going to take a little longer. So this is still going to kick me out into that, after it does its initial calculation, it's going to kick me out and process in the background. I'm free to go on and start programming my next toolpath. So if this was a huge part, that calculation time isn't really holding me back from being productive. So that's a big part of this is implementing that, that background processing. So now we look at our initial toolpath, and then we display the second one. Let's display that second one, right? Now I have to actually zoom in to see how tight that G code is. And that's really where that Makino is going to excel with all those points right on there. It's going to rip right through that code. So I hope that answers your question, Greg. Some of the stuff that we're doing in Mastercam, that's the quick answer. I could go on for hours probably on that one subject. But
No, that's great, Jesse. Thank you. That helps quite a bit. I do have another question, and for our group, we do a lot of sample parts, or we'll actually cut parts for customers to show them the performance of our machine. And one of our challenges is always to show, the best surface finish possible. So, a lot of times when we're looking at these parts, visually the best way to do that is a lot of times to create toolpaths that follow the feature. So if you do that, there's some benefit there that you're keeping the tool down on the part as much as possible. There's less lifts, and then again visually it just looks a lot nicer because the pattern matches the shape of the part. So I guess my question to you is a lot of toolpaths, standard toolpaths like a raster or parallel, constant Z, or waterline, they really have what I would consider a fixed pattern or no ability to kind of change that motion. What does Mastercam offer that can kind of take me to the next level to get that ultimate appearance? And also, is that capable of being done in 5-axis?
Yeah, that's again a really good question. The toolpaths you mentioned, waterline, parallel, raster, those are all very rigid in what I'd call cut pattern. So that's like what Mastercam draws is the little blue lines on the part, right? So that cut pattern, I mean, it's by definition. With waterline, we're taking Z heights and we're putting that waterline on the part. So that's what it's going to cut. It doesn't care what the feature looks like. It's just stepping down in Z and putting those lines on the part. Raster is very similar, but it's doing a top-down projection of those lines on the part, oriented in a specific direction. It's not going to change based off the feature. So those toolpaths, I don't want to discount them at all because they're classics and they're at the top. They're my go-tos when I'm programming. It's when you start getting into those special situations that you described where you've got this weird, a weird shaped surface or patch of surfaces that you need to program, and doing that doesn't really make sense. And that's when you start looking outside of this for something else. And one of the things that I think addresses this a lot, especially we'll talk about the 5-axis in a second, but in the 3D world, which is still the majority of die mold, right, is the blend toolpath and the work that we've done in that recently. We've always had the old 2D blend toolpath, but I think it's valuable to look at the newer version, the new stuff we've developed, and I think it addresses a lot of what you just brought up because there's a lot of issues with what the old blend toolpath could and couldn't do. So I think the best way to do that is probably to just jump into Mastercam here and show you. And I've got these, we'll look at this same part file here. Minimize these down so I can see what I'm working with. So if we look at these, those orange surfaces, right? Say we were to program that shape. If I did that with a waterline or a raster, I think it's pretty easy to visualize what you'd get there, right? You'd get a lot of partial passes down in this narrow section with larger passes here, a lot of lifts. You'd have a lot of retracts coming across the part. Your linking would be probably subpar. So if we went, let's go back a few versions ago, if we looked at Mastercam, our options in a 3D realm would be the blend toolpath. Well, if we use the standard blend, I'm going to shut off advanced display. If we use the standard blend, we get a pretty decent toolpath there that comes around the part. Big issue there though, right? I've got to get into making all these fancy drive surfaces to make it work properly, because when I start this toolpath, right, look at where it's going to contact the part. Let me step along here, right? Where it first makes contact with the part, it's all the way up on that surface. Now, I'm programming that entire orange surface. I expect that tool to come down to the bottom. Why is it not doing that? Well, blend is basically, if I shut this off, is basically going to be doing a 2D projection. If we look in the top plane, you can see exactly what it's doing. It's taking that outer edge, that inner edge, blending between the two, and projecting from the WCS Z, the Z orientation down on that part. So that creates issues because we're not getting down all the way on the surface. Same issue up here, right? We need to roll over that edge with the contact point of the tool. So let's take a look at the new blend toolpath and what that has to offer. Now, if I started from, this is the new blend toolpath, and I think one other thing I want to point out here is the blend toolpath, the new one, has a 2D and a 3D option. So we're going to look at the 3D. The 2D works very similar. It's replacement functionality for what the old blend toolpath does. The 3D functionality does a 3D projection on that part. So it's looking more along those vertical edges, and it's gonna better keep that step over across those vertical portions of the part, like this bottom edge here. If we backplot that though, right, you'll see a very similar issue, right, where we're not getting all the way down to the bottom of that surface. So that this 3D blend at the surface looks like, well, now it's not, it's really not doing what I wanted. But because we're leveraging the new 3D HST toolpaths and the interface inside of Mastercam, we have some other options to address that. So if we go into the tool control tab, there's this tool contact point. By turning that on and looking at the toolpath, right, what that's doing is it's for the edges of the surface, it's looking now, instead of the center of the tool or that tool tip, it's now looking at the contact point of the tool, right? So it's going to run down the surface a lot further. If we come up to this top edge, it's going to roll over that edge now, where the 2D blend does not have that capability without going in and drawing all these surfaces to get it to run off. Just not ideal. Now, the second part of your question, you were talking about, can that be used? I think that addresses the cut pattern side of things that you were talking about with using a blend like that to meet those parameters. But the second part of your question about whether that can be used in 5-axis, I wanted to point something out. So if we take that same toolpath and we shortened up the holder and we look, let's come down here, right? You can see the holders hitting the part here. So my options typically in 3-axis would be what? Get a different holder, a slimmer holder, or have a lot more tools stick out. Either case, not ideal. You're probably introducing chatter. Your surface finish is going to suffer all those different things. So because we're now pushing that blend into the HST environment, that's going to allow us to use our holder checking inside of the HST toolpaths. So now I can say, all right, I turn on collision checking. I want to leave a millimeter around that whole holder, and I'm going to give it up to 25 degrees. I'll let that let that tool tilt away from the part. All right. So the result there is, well, now we've got, look at, we're leaving a millimeter between the part, and we're tilting where we have to, but then we're staying 3-axis where we don't have to. So that allows, basically, if I know how to program 3D and use these 3D HST toolpaths, I'm programming a multi-axis. Pretty neat. Obviously, you don't have full control here. This is kind of, you're letting the algorithm decide how to avoid those surfaces from hitting them. You're not in full control what that tool axis control looks like. You can't really understand. You can't really control exactly how the rotaries are going to move on the machine. You're at Mastercam's mercy of what it thinks the best way to tip away from those surfaces are. In some cases like this, it works beautiful. Sometimes it's not an ideal situation, and that's when we move into our true multi-axis toolpaths. So here we're going to look at a morph toolpath, which gives me a very similar cut pattern, but now I can intimately control that tool axis strategy. So here I'm going to say, all right, I want to stay normal to that surface at all times. And now I have a 5-axis machine, so I can do that. And I also want to give a little lead. I'm going to give 10 degrees of lead on the tool so that I'm not on the tip of the tool, right? If I stayed normal all the time, I'd be right on the tip of the tool. I don't want to do that. So I'm going to tip off 10 degrees, and that's going to give me a really nice sweeping motion in full 5-axis along that part, right? Really slick tool path there. That's going to look beautiful running on the machine. And because I'm in simultaneous 5-axis all the time, my surface finish is going to be very consistent across the part. The tool contact patch is not changing with respect to the surface, whereas with that 5-axis multi-axis tool path, that contact point is shifting. Your surface footage, your chip per tooth is changing depending on where you are in the surface. That's going to change that cut pattern. So there's advantages in that it's easy. There's also disadvantages in where it makes sense to move over to the full simultaneous 5-axis. So that was a long-winded answer, but I hope that that addresses some of your concerns, Greg.
Yes, that was great. That's exactly what our engineers like to see, and I like the fact that in the full 5-axis, you guys are, controlling exactly where in the tool that it's making that contact, because that actually is very critical to, achieving your, your calculated surface finish consistently. So that's great. One other question I have is that, with all that 5-axis motion, if we're talking about the Makino D200Z machine, that machine's got a rotary speeds of, 150 RPM, rapid traverse feed rates of 60,000 millimeters per minute. It's a very fast, compact machine. You guys had this machine in your R&D lab, so I guess I just wonder if you could expand on it a little bit, that how you ensure that you're not going to have any issues, because at those feed rates and that speed, the days are just gone of where guys can be standing next to the machine with the cycle stop button or the e-stop and trying to stop it before he thinks there's going to be an issue. So the machine's just too fast. So how does Mastercam ensure there's not going to be any interference issues?
Yeah, Greg, the first time I saw that 200Z in full rapid, it's eye-opening. There's no chance of reacting to something going wrong. So you got to have confidence in that your code is right, and you got to have the tools in place to make sure that's right, because bad things are going to happen really quickly on a machine like that. That's that quick. It's just how quickly it moves almost defies physics, right? It's insane. So, we utilized a couple different solutions, and Mastercam offers a few different ways to address this. I think the most critical and most important aspect of all of this is a good post processor, right? The post processor we were using in here for our D200Z was the result of a collaborative effort. The post was developed by Postability, a third-party post processor vendor for Mastercam. It's a very intimate partner of ours, and it was vetted through our testing. And when we got in the machine, it was also recommended via your applications team. Basically, I mean, this is the post that you guys are using that you tested. We were also able to recommend, some improvements, some changes from our end, and we came to rely on that post, and we're confident in its power and its accuracy, right? However, if I don't really know what I'm doing from a programming side, and I hand a poorly programmed part off to a fantastic post processor, I'm going to still have bad code. I can still crash the machine, right? Without really, if I'm uncomfortable with that sort of thing, it can happen regardless of how good the post processor is. So I think that's where, the tools we have inside of Mastercam with backplot, with verify, with machine simulation, they come in. We in that couple examples I showed you, I was using backplot there. It easily visualizes the toolpath. It makes a quick, it's easy to compare what's happening between toolpaths, what the motion is. But it has shortcomings. It's not going to show you collisions. It's just showing the raw tool motion and the vector that the tool is at. Mastercam Verify does a more thorough job. It's going to show you stock removal. You can see machine part comparisons to what you've actually cut, so you can start to get a feel for surface finish. It'll show you potential collisions with the stock or the fixturing, basically the stuff that you've defined inside of Mastercam. It's not going to show you. It's kind of shows you everything you need to know outside of how that machine is going to move. So that's where we bring up machine simulation, right? That's going to bring all the machine components into play. Is that spindle going to hit the table? The machine simulation, that's the best method to find out prior to post-processing that allows for those changes while programming the part. I'll often use machine simulation too for like exploration purposes. I see the part. Well, okay, how do I want to program this? Do I want to, come from this direction? Do I want to cut it this way? How's that going to look on the machine? Well, I dump it into machine sim, take a quick look at it, right? It's an invaluable tool to see what works and what doesn't. So I'm just going to show you, kind of what a machine simulation would look like, the functionality inside of Mastercam. And this is the Makino D200Z. And if I run this, right, I'm actually looking through the glass just as the operator would, and I get to see, how that machine's going to look. This is that 5-axis morph toolpath that we just programmed at the end of that last example here. And we can see how that motion's going to look. And I mean, that looks really nice. The other cool thing with machine sim that I can't do with the real machine, right, is I can shut off all the components I don't care about. I can get inside the machine. I can look from the backside and understand how those Z-axis way covers are going to look against the table. This is where I'd understand if my holder was too short. I could see, that Z-axis smash into the rotary table, and I'm doing that on a virtual twin. So when I smash into that Z-axis, nothing bad happens, right? I go in and I say, oh, I want a 2-inch longer holder, right? So it's really critical, and it really works well to understand, and then keep in mind, this is all prior to post processing, which there's an advantage there, right? Because now I can see what's going to happen, and I can go back and make changes and then test again to make sure that's going to fix it before I go through the whole post processing and all that. Now, there's also a couple other solutions that, they're not native Mastercam, but there's things that we use in our shop to increase confidence at the machine, especially when you get into that 5-axis realm. And one that should really, from a Makino side, one that should really pique your customer's interest is Vericut, right? I mean, Vericut is to G-code simulation or G-code verification what Mastercam is to CAM, right? It's the industry standard. So, Vericut's a good partner of ours at Mastercam, and the awesome thing about Vericut is its seamless integration into the CSG interface. I know you mentioned that before. That resides right on the Pro 6 control. So we can easily transfer the Vericut files. Once we do that Vericut file, and once we do that Vericut verification, on our PC, we can transfer that right to the Pro 6, right to your control. And then that's a powerful defense against machine collisions, because when you just do a Vericut all by itself, oh, it's great. I don't have any collisions and I don't have any issues. But then I go to the machine and I fat finger an offset. I meant to put 4 inches in for that tool offset, and by accident I put 0.4 inches. Well, that's going to be a big difference on that offset. So this is verifying live those things happening on the control, and that's your last defense against machine collision. And typically, if you're using Vericut, you already did the work there. You've already verified it. So taking that last step is another insurance policy there. You don't want machine downtime. A stationary spindles, especially a broken one, is certainly not going to make you any money. It's going to cost you money. So I hope that answers that question.
Yeah, thanks, Jess. That was great. And in fact, it's an excellent explanation of collision safeguard on the Makino machines. It's catching those last couple bits of information, the tool length, fixture offset, all those things that you can't check virtually, in Vericut on the computer. So thanks for that explanation. So in the last 4 more years, we've seen tooling technology changed quite a bit too. Also, we've seen the multi-flute, 6-flute M mills, and hybrid tools being used in the the die mold industry. So the multi-flute, 6-flute tools, the ball noses that we've seen, they give us great improvements because we can run at much faster feed rates, and that's where our new Pro 6 control with the SGI 5, we're seeing 13% better performance compared to our previous generation, so we can maintain these higher feed rates. However, the hybrid tools are a little bit different because you have these unique shapes where you take a barrel tool that has a larger outside radius that goes tangential into a point, or a smaller radius. That larger radius gives us the ability to, at a given surface finish, compared to a smaller ball nose tool, to have a larger step over, thereby reducing your cycle time drastically. There's also other benefits of being able to blend with that smaller tip radius into smaller internal features, potentially eliminating subsequent tools on certain features. But I guess my question is we have these very unique shaped tools. How's Mastercam able to support this complex geometry in these tools, kind of moving forward, making it easier on the CAM programmer?
Yeah, great question. It's a really talked about aspect, kind of a hot subject inside of the industry and CNC machining in general. I'll first answer. I know you talked about the multi-flute, the feed mill type tools, and I just want to share my experience with that on the D200Z. I did a part, I want to say recently, but it was probably a year ago now, with this car, one of their new nano feed insert feed mills. So we're talking about a little 8mm insert mill with these tiny little, barely see them on your fingertip, these tiny little inserts that allow you to go really fast into small features, right? And use the same advantages that a standard feed mill would use, but we're also doing it on that precision die mold machine that has the high RPM on the D200Z. You're in the realm of where that machine excels, right? Because it's not a high horsepower hogging machine. The results were phenomenal. The feed rates that D200Z could maintain to keep that chip load where that tool needed it to be. We were doing this in hardened stainless. It was insane, right? With the SGI activated, the machine had no issues maintaining feed rates, which is where we needed them to be in the 500 inch per minute range. Now, 500 inches per minute, you might say, oh, any old machine off the, any old machine can do 500 inches a minute. That's nothing. But we're talking about complex geometry in a part that was less than 2 inches square, right? So, I mean, the speed that that machine is going at those small segments of linear rate, we're talking about tons of directional changes, and that machine is just whipping through them and reading the code incredibly fast. So it was really impressive, and the tool survived. Couldn't kill. I never had to even rotate the inserts because it was putting the tool right where it needed to be, and to do something like that, you need everything working together, right? You need that high end machine tool, you need that high end hardware, but you also need the high end control. You need that control capable of commanding that hardware to do what it needs to do, and they all need to be working together as a system, and you need to be feeding it the right code, right? And that's where the CAM system comes in. So all that stuff has to be working together, and I think Makino and Mastercam, we kind of offer that solution. So we were able to utilize those cool new tools. As far as the other specialized large radius tools you're talking about, there's a lot of industry buzz around them and a lot of different names. So here at Mastercam, we've kind of called them accelerated finishing tools, and the algorithms that drive them, we're calling those, accelerated finishing toolpaths. We're not designing toolpaths specifically at these tools. We're allowing you to leverage these tools in our existing toolpaths. So the same things you program a ball end mill with, those familiar toolpaths, that's what you're using to program these accelerated finishing tools. You know, parametrically defining and properly compensating to these, strange tool shapes, it's not the norm. It's not how CAM systems typically worked when we were only programming ball end mills or flat end mills, right? That's super easy compared to what these tools are, and getting the compensation rate right is very difficult. So a lot of work went into not only the tool manager side, but also in the toolpath algorithms to properly support these tools. I've seen real life examples of these tools realizing, in the right application, 70% cycle time reductions, and still getting still meeting the same surface finish requirements they were getting with a ball end mill. I've got a PowerPoint presentation here that I'll go through quick to just kind of talk through what these tools do and get a better understanding here. And really what it all comes down to is, challenges of traditional machining or traditional finishing. When you're finishing a part, that's always going to be the most time consuming segment. And it's not only the most, we have the tools now with OptiRough and dynamic motion technology where the roughing now is easy, right? It's just going to eat all that material right off of there. The tooling has come to a point now, you talk to the right tooling vendor, get the right information, you're running dynamic motion. Roughing is not a big deal. But finishing, that's the most time consuming thing. You're stepping over a ball end mill in these tiny amounts. And it's also the most important segment of any machining project. And why do I say that? Well, when you hand a customer a finished part, they're not buying your roughing strategy. I mean, unless you're in aerospace where they're tracking, how that whole strategy comes. But in most cases, people are buying your finish, your surface finish. And to get that better surface finish, it's more time, more money, right? So this is an example of a beautiful surface finish, but it's done, with a ball end mill at a 2,000 step over. Very, very time consuming. To understand how accelerated finishing can cut down on cycle time, you need to understand what cusp height is and how your cutting radius can affect that. So there's two solutions to minimize cusp height. One is to decrease the step over amount, and the other is to increase the cutting edge radius or the contact patch of that tool against the part. The side effects of decreasing the step over is, you get a cycle time increase. That cycle time is money, right? And then the other side effects of decreasing that step over are you get a bigger NC file size. When we're talking about a machine, like the Makinos with the Pro 6 on it, who cares about the NC file size? So the machine can read. It doesn't care if you've got 7 million lines of code. It's going to be fine. The biggest thing is that cycle time increase. That's what we're chasing. We want to minimize that as much as possible. So to understand cusp height, let's look at a 6 millimeter step over, and we're left with a cusp height that's 1.2 millimeters, right? If we take that same step over and we increase the tool diameter by 4 times, we can cut that tool the cusp height down, the waves that are left in the part, by a third. I mean, that's huge. That's a huge effect on surface finish. So why don't we just swap out every little tiny ball end mill we've got with a large one? Well, there's a reason we're using that small end mill to begin with, right? You can't get into certain areas. You have reduced reach. You're leaving material in the corners, and you've got potential collisions when you're using a larger tool with other features. So that's where accelerated finishing was born from. I mean, obviously, we didn't invent this concept. It's been around. Everybody understands that the larger tool leaves a smaller cusp height. The accelerated finishing is really the application of special tools, circle segment tools, inside of Mastercam on your part. And the biggest part of that is applying the necessary compensation. You get the compensation right, you allow yourself to get a better, higher quality surface finish in less time. So the biggest thing, if we look at this animation here, I mean, this is the biggest part of it. It's proper compensation. You're not going to cut this part like this, but this animation is showing, this is done inside of Mastercam. It's showing that we can comp to all sides of that tool, which allows us to, get those cycle time performance increases, as well as getting a better step over or a better surface finish. The accelerated finishing supports there's 5 new tool types inside of the tool manager: barrel form, oval form, taper form, lens form, and then one of the newest is the lens barrel form. And we're continually adding new tool types to this as we go through. Here's a quick case study that we machined on our 200Z. This is showing the lens tool type on this part. And when we did it with traditional finishing, we were looking at 1 hour and 11 minutes. Just implementing the lens tool, we went down to 46 minutes, so a 35% cycle time improvement. The big difference there, if you look at those surfaces, is they're practically mirror finish, right? The surface finish, even for the same cusp height, the surface finish was just so much better, just because you're using a larger, more stable tool. So we went from a finish that had to have some handwork and polishing to one that was ready to go right off the machine. So, and in less time, right? So one common misconception that I want to throw at you is one of the things where we say, all right, well, let's throw away all our ball end mills. Why are we using balls anymore? Let's just use these circle segment tools. And that's incorrect. You're always going to need the ball end mills for that finish work in small areas. That the part geometry really has to lend itself to the use of these tools for them to be effective. And oftentimes the best place to use these tools are on large flowing surfaces that have a low rate of curvature change. The great thing about that is those are also the surfaces that are going to take you forever to machine. Those are going to be your highest cycle time concentrations on any given part. So that's where these tools fit in. That's where you're going to see the gains. I think we're not quite done yet. I think we've got time. Yeah, we've got time for one more quick question, Greg, if you've got one, and then we're going to wrap this up.
Great, thanks, Jesse. I just want to touch upon something you mentioned earlier about the post-processors and that partnership that we have with you. And from my perspective, and I think from our customers' perspective, that's so important, because a lot of customers we're dealing with are actually new to 5-axis. So the fact that we've kind of proven that post-processor out between us before it got to the customer is critical, because, like I said, a lot of these customers are very new to 5-axis, and for them to learn it on their own takes a lot of time to learn those new techniques. But it also raises another concern that I hear a lot from our customers is that, going to 5-axis is so much more intensive as far as programming. So I guess my question to you, Jesse, is what can you tell our listeners here today that going to 5-axis is not that great a leap. You can build upon what you already know in 3-axis, and that Mastercam has these intuitive tool paths that can really reduce the learning curve and make that leap very easily.
Yeah, Greg, I think, I hear this all the time, and I think we kind of touched on some of that already when I was showing the blend toolpath on this mold cavity here that I'm showing on the screen, where you can, with 3-axis experience, you can program 5-axis with that holder checking. I think that's huge. That can kind of get people's feet wet into the multi-axis world. The thing I don't like, and the biggest issue with that method, is if you say this is the only way I'm going to 5-axis program, you're kind of stonewalling yourself into a corner functionality wise, right? It's a very simple way to program 5-axis, but it's inherently limited because of how simple it is, right? We couldn't control exactly how that tool or how the machine moves, which we can do in our full out multi-axis toolpaths. One thing that we've kind of taken a leap towards in recent releases is what I'll kind of call semi-automatic toolpaths. So things like Mastercam's deburr toolpath, the new swarf milling toolpath, port expert and blade expert, and the new multi-axis pocketing toolpath, which is new for 2021. That has the ability to kind of coach you down the path to give you the results that those tools that you're using would want, and kind of setting up the parameters. It's like I said, kind of semi-automatic in that it you don't need to know every intimate detail about multi-axis programming to get results, and I think that's important. Um, I think that question about 5-axis difficulty, it comes up a lot, and in talking to a lot of customers, I think the root of that issue of taking that next step is fear. Really, I mean, what I tell people all the time is, if you're an experienced 3D programmer and you're programming 3D surfaces all the time, you at one point were only programming 2D. I mean, that's the typical evolution, right? Whether it was at trade school or your first job, or you did it for 20 years and then you moved into 3D, at one point you made a transition from 2D to 3D. And I don't see the transition from from 3D to multi-axis much different than that 2D to 3D transition. And the difference, I think one of the biggest differences there is if you take a typical 2D programmer and a 3D programmer, that 3D programmer typically has way more experience. They understand tooling. They understand the concepts of CNC machining. They're more familiar with the machines, the controls. That can all be used as an advantage when transitioning to multi-axis. So I almost think you've already learned a good portion of what you need to know to make that transition. I think the biggest issue is that multi-axis is not as familiar, right? Every shop on the block is running 3D parts, with 3D surface finishing all over the place. People see it all the time. A much smaller subset of people are doing multi-axis every day, day in, day out. And if something's unknown, it's people's tendency to be fearful of it and make it a bigger deal than it is. I think the biggest thing you need is resources, and our applications team here has been working a lot recently, producing a lot of video content on YouTube. I mean, even things like this webinar we're doing, which will be available on YouTube, just to reference and kind of give some familiarity to the subject and encouragement that you can do this. And I think the industry is changing. Like you kind of mentioned at the beginning of all of this, it's no coincidence that Mastercam's multi-axis licenses are one of our top growth products for a few years running. And I don't know whether you're seeing the same thing on machines. I kind of assume you are, based off of the comment you made about that transition. So you're probably seeing more 5-axis machine sales. Is that true?
It's very true. Yes.
Yeah. Yeah. So I think it's a big shift, and I mean, people can resist it if they want, but it's coming, so you might as well embrace it and figure it out. And I think that's the biggest hurdle is just say, I'm going to figure this out and, take some test cuts, take it slow, figure it out, use the tools that, Makino and Mastercam provide to make this easier, make that transition easier, and just do it.